Okay, so section 10.5 is on probability. We talked about probability time now. We've never talked about permanent here, but we're going to introduce. How many outfits? Let's use it to find how many outfits. We have 6 pairs of pants, 2 pairs of shoes. Okay, so the tree diagram is already here for us. We just got learning about tree diagrams in the first part of chapter 10. They say we have 4 sweaters. That we have 1, 2, 4 different branches for 4 sweaters, right? We have 6 pairs of pants. We have 1, 2, 3, 4, 5, 6. And we have 2 pairs of shoes. So we have, let's go 1, 2. Right? So the tree diagram is showing us all the options. If we draw the complete tree diagram, we would have the total number of outcomes. How this would work. So if we go all the way to the end of our pathways, so let's say we went sweater, pants, shoes, that would be one pathway, right? And we'd have 1, 2, 3, 5, 6, 7, 8, 9, 10, 12 different. And we'd have the same 12 different pathways for each of the 4 different branches. So 12 times 4, 48 total possible outcomes. Well, there's another way to come up with this number also, an easier way, where you don't have to draw the tree diagram and have that visual of every possible outcome. And the way to do this is we take the number of sweaters, 4, times the number of pairs of pants, 6, times the number of pairs of shoes, 2, and we multiply those together and we get different possible outcomes. Now this has a name. We call it the counting principle. And it says the number of ways in which a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. So in the example that we just did, the counting principle, to find how many different outfits we can get, we took the number of different ways we could choose a sweater, times the number of different ways we could choose a pair of pants, times the number of different ways we could choose a pair of shoes. We multiplied those up, and we got the total number of different outfits that we possibly could come up with. All right, so let's apply this to a couple more examples. It says, suppose a set of license plates has any 3 letters from the alphabet, followed by any 3 digits. How many different license plates are possible? To find how many different we can have, every license plate in this scenario is going to start with 3 letters. So I'm going to draw a box for each letter. That's going to be a letter. That's going to be a letter. Then it's going to be followed by 3 digits. Well, I'm just going to put a dash there. And then I'm going to put a box for each digit. Now the question is, how many possible options are there for each of these positions? So in the first position, right here, how many possible letters could go right there? 26 letters in the alphabet, any of the 26 could go there. The next box represents a letter also. They didn't say that we can't repeat letters, so I guess we can. So any of the 26 letters in the alphabet could go there also. And the same with the third position where a letter goes as well. Then we have the next box representing a digit. Well, 0 through 9 is 10 different digits. And they didn't say that we can't repeat digits, so I guess we can. So we could have 10 possible digits there and 10 possible digits there. So what we've done is we've come up with every possible option in each position, and now we're going to multiply them all together to get the total number of license plates. Again. Okay, so part A, we got the total number of license plates. In part B, they're asking us for the probability that a license plate has no repeated letters or numbers. So we're transitioning from the number of possible outcomes up here to now a probability problem. So let's find the number of license plates that have no repeated letters or numbers. We can set this up very similar to part A, because in order to find the probability, we have to find the number of license plates that don't have repeated letters or numbers. So let's draw our boxes again. And the only thing that has changed now is we cannot repeat letters and numbers. Any of the 26 letters could go in the first spot. But once you use a letter, you cannot use it again, because they said no repeat letters, right? So now there are only 25 letters left to choose from. Once you use that letter, now there are only 24 letters to choose from. Any of the 10 digits could go here, but once you use a digit, you cannot use it again. So now there are only 9 digits left to choose from. And you can't use that digit either again, so now there are only 8 digits to choose from. So we multiply these numbers together, that's what the counting principle tells us to do, and we get 11,232,000 license plates would not have repeat letters or digits. Now we can get the probability by simply taking that number over the total number of possible license plate, which we found in part A, and as a decimal, 0.639, and as a percentage, we'll say 63.9%. So 63.9% of the license plates do not have repeat letters or digits. All right, now we have to go back and we have to review factorials, because factorials are going to play a part in permutations. And if you don't remember what a factorial is, that's okay. They're not used all that often in math, but certainly are used sometimes in probability. So our first example here, this is read 5 factorial. You can see the exclamation point. We don't call it an exclamation point in math. It represents a factorial. And what a factorial is, it's when you take the number that you see there, 5, and you multiply it by every number less than it down to 1. So times 4, times 3, times 2, times 1. So 5 factorial equals 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Could multiply all those numbers out. That wouldn't be that hard. But there's a factorial function on the calculator. So if you have a TI-84, if you hit the math button on the left side and you go over to prob, P-R-O-B, for probability, it's number 4. You see the exclamation point, which is the factorial. You can type in, go to your home screen on your calculator, type in 9, and then go to that factorial function. End up with our answer, 362,880. In number 3, 0 factorial always equals 1. All right, a couple more here. In number 4, we have 3 factorial, 4 factorial. This means 3 factorial times Now, we can do this on a calculator, but we need to know what it means. 3 factorial is 3 times 2 times 1 times 4 factorial, which is 4 times 1. So you could just multiply these numbers out, or you could grab your calculator and type in 3 factorial times 4 factorial and get the same answer. It equals 144. Number 5. Again, you could type this into the calculator, but I'll tell you this, you need to know how it works, because when we get to number 6, the calculator won't do it for you. So pay attention here, number 5. 26 factorial. We know that that means 26 times 25 times 24 times 23 times 22 times 21 times 20, all the way down to 1. And it's being divided by 21 factorial, which of course would be 21 times 20, all the way down to 1. So in this case, we have 21 factorial right there, and we have 21 factorial right there. So to do this problem, you could just type in 26 times 25 times 24 times 23 times 22 and get your answer. Equals 7,893,600. All right, so now we're ready for number 6. If you type this into your calculator, you will get an error message and it'll say overflow because the numbers are way too big. But since we understand number 5, we know how to do number 6. In number 6, 500 factorial, we know, is 500 times 499 factorial, right? It would go all the way down to 1. Well, the denominator is 499 factorial. So those are going to cancel each other out, and our answer is 500. All right, we are now defining permutation. A permutation is an ordered arrangement of items that occurs when no item is used more than once, and the order of arrangement makes a difference. There's a formula for permutations. The number of permutations of n objects taken r at a time equals n factorial over n minus r factorial. And it's important to note that all permutation problems are also counting principle problems. Now you see the use of factorials in this formula. Okay, that's why we reviewed factorials. But the calculator has a permutation function on it. So you are not going to be required to use this formula. It's really here just to show you that it exists so that you have some sense of the math behind what the calculator is doing. Grab your calculator and hit the math button again. Go over to probability. It could be PRB or it could be PROB, depending on what software you have on your calculator. And look at number 2 right here where it says NPR. That's our permutation function right there. That's what we would use if we were calculating permutations. So let's say that we had an example where we had 9 objects and we wanted to find out how many different ways we could arrange 4 of the 9 objects. Then on our calculator, we would type 9. Then we would go to the permutation function on the calculator, type that in, and then we would type 4. And the calculator would calculate that if you have 9 total objects and you want to find a number of ways to arrange 4 of the 9 objects, there are 3,024 different ways to do that. So an example using permutations. 7 flute players are performing in an ensemble. The names of all 7 players are listed in the program in random order. What is the probability that the names are in alphabetical order? All right, this is a probability problem. They're asking us for the probability that the names are in alphabetical order. So we're going to find the number of ways to list them in alphabetical order over the total number of ways to list the 7 flute players. How many ways can you list the names in alphabetical order? There is only one way that those names can be listed in alphabetical order. Now we have to find the total number of ways that those 7 names could be listed. This is going to require the use of permutations. So we have 7 flute players. We want to know the number of different ways to arrange all 7 of those names. 5,040 different ways to arrange those names. So the probability that they are arranged in alphabetical order is 1 out of 5,040. After the performance, the players are backstage. There is a bench with room for only 4 to sit. How many possible seating arrangements are there? Okay, so we now have 7 flute players back there, but we're only going to arrange 4 of them on the bench. So they're asking us for how many different ways can these 4 flute players be arranged on the bench. So we have 7 total flute players. We're going to arrange 4 of them. That's 7p4. We can plug that into the calculator. There are 840 different ways that 4 of the 7 flute players could be arranged on that bench. Finally, we go to part C. What is the probability that the group of 4 players is sitting in alphabetical order? So again, there's only one way to arrange the 4 flute players that sat down in alphabetical order out of a total number of 840 different ways that 4 flute players could have sat down on that bench. So the probability is 1 out of 840.